Alex, and good afternoon, good morning everybody, depending where you are. Maybe I can add to your introduction that my major research interest covers navigation in chemical space, bioisosteric design and development of web tools for medicinal chemists. And actually in my presentation I will unify all of these three my hobbies into this presentation. I will speak about rings in bioactive molecules. Why to focus on rings? Basically, rings and scaffolds are probably the most important part of bioactive molecules. They gave these molecules their basic shape and keep substituents in their proper 3D position. When we look at the bioactive molecules in the ChEMBL database, no wonder 98% of these bioactive molecules contain at least one ring. Here you can see the motivation for my study. At the beginning, I simply wanted to ask myself this simple question: can we identify such rings that they are present more frequently in bioactive molecules than in synthetic molecules? And if the answer to this question is yes, I did know at the beginning. It is possible to identify some simple structural features that simply distinguish bioactive rings from these common synthetic rings. If we can somehow handle this or answer this question, you can imagine this may be pretty useful for drug discovery process. We can simply use it in the purchasing potential active molecules to enhancement of company molecular collection. We can use it in virtual screening, in library design, synthesis of DNA encoded libraries, in hit optimization, and so on and so forth. Just name it. So in my study, I look at the rings in different molecular collection. For that, I use the cheminformatic technology that is called substructure analysis. That is nothing really new. This is substructure analysis, is classical old method. This has been developed maybe 30 years, maybe even more than 30 years ago. The basic principle is that we simply look at our molecules, cut them into meaningful pieces, and then we analyze these different substructures. We can focus on different types of substructures. Here you can see some examples. Probably the most important part on the left in orange, this is the scaffold. Scaffold is simply part of the molecule when we cut away all non-ring substituents. The scaffold itself consists of, we can see this on the right, of a ring system. These are this light blue part connected by a linker. Linker is non-ring part, non-ring atoms connecting the ring system, and ring system themselves are either simple one ring or collection of fused or spiro ring, like in this case. In this presentation, the rest of my presentation, I will focus on this ring system. So when I will speak about rings or ring system, that's it. And of course, we can use different other types of fragments in substructure analysis. You can see this at the top: functional groups or substituents, and even fingerprints. There are many possible types of such substructures. But as I said, in this presentation, I will speak about ring system. Here we can see some examples of the parts of the ring system I deal with. I extracted this ring from two large collections of molecules. From the bioactive molecules of the ChEMBL database, I suppose most of you are familiar with ChEMBL. This is really indispensable resource for medicinal chemistry and cheminformatics. Current ChEMBL has about 2 million molecules, and about 700,000 of these are bioactive. This means that activity is better than 10 micromolar on any target. And another collection I used for extraction of rings, this is this famous ZINC database of commercial available molecules. ZINC is a really huge database containing about 1 billion molecules. So actually I extracted ring system from about 1 billion of molecules and was able to extract 40,000 rings. Here you can see some examples, very simple system, just with one ring, like this one, fused system connected by the single bond with 2 atomic bond, but also some non-classical ring fusions like something like this. And we can see also several spiro systems here. One important thing, you see this by yourself, this double exocyclic double bonds we are keeping, these are parts of this ring system because they really are very important. Removal of these double oxygens would simply change character of ring system. They would change from aromatic to aliphatic, and that would really change considerably these ring properties. So these exocyclic double bonds are remaining. Here on this slide, you can see the most common ring systems that are present in bioactive molecules. I told you before, the 700,000 molecules from the ChEMBL database. And we can see here a lot of old friends. The most common is phenyl, pyridine, piperidine, piperazine, and so on and so forth. But actually, this is not what we are interested in, because phenyl will be, or benzene ring will be probably the most common, or is the most common in practically any molecular collection. What we are interested in is not the rings that are absolutely frequent in bioactive molecules, but they are relatively more frequent. That is, they are more frequent in bioactive molecules than in standard common synthetic molecules. So we need to compare these two distributions. Here we can see one example of this. On the left side in this green frame, these are what we have seen on the previous slides. These are the most common rings present in bioactive molecules. On the right side, these are the most common ring present in this synthetically available, commercially available molecule from the ZINC database. And when we compare these two sets, well, they are pretty similar. We do not see too many differences. As I told you before, phenyl ring is always first. On the left side, pyridine is second. On the right side, pyridine is fourth. Piperidine third. Here is second. So the differences are not so distinct. And of course, one cannot do such comparison for, let's say, several hundreds molecules by looking into the two tables. So we need to do this in a little bit different way. And this is how we can do this. This graph is already more informative. On this graph, I have the 80 most frequent rings from the bioactive molecules and 18 most frequent from these synthetic molecules. Altogether, I think this is about 120 unique rings. And on these graphs, on this x-axis, there is the frequency or popularity of the rings. On the left side, we are rings which are very, very common, like this phenyl and so on. On the right side, they are also common, but maybe slightly less common than these on the left side. And what is interesting, on the epsilon axis, this is somehow something like propensity of these rings for presence in bioactive molecules. Basically, this is a ratio between the frequency in bioactive molecules and in synthetic molecules. This green area at the top, we can see rings which are much more frequently present in bioactive molecules than in synthetic molecules. And that already, this graph provides already quite interesting information. We can see that these rings typical for bioactive molecules are the mostly fused aromatic rings with many heterocycles with mostly nitrogen. On the other side, here at the bottom, these are rings that are typical for synthetic molecules. These are mostly aliphatic system. Some of them are quite exotic like these spiro systems here. And in the middle, in this area, when this green and red color overlaps or merge, we can see rings that are of no great interest to us. These are rings which have the same frequency in bioactive molecules and synthetic molecules. So let's have a look at this top area, this green area, and take, I think, 100 these green rings. And we can see another visualization of these bioactive rings. And in this visualization or in this picture, I try to color-coded these rings based on the preferred target for molecules in which these rings are contained. We can do this. We have the ChEMBL database. In the ChEMBL database, we have the literature source. In this literature source, also we have the target protein. In ChEMBL, there are about, I think, 17,000 different target proteins. And then maybe they may be classified into these 8 classes, or I classify them into these 8 classes shown here: GPCRs, kinases, proteases, nuclear receptor ion channels, and so on and so forth. You see this. And in this graph also, I try to cluster these rings based on the similarity, based on the fingerprints, so that you see that similar rings are grouped together. So that's already quite useful. Visualization helps us to start to see, navigate, or start to navigate in the ring chemical space, maybe even to identify some analogs and so on. But still, this is not what we want, because theoretically what we want is a system which would be interactive, not such just a static picture. We need to visualize not 100 images or 100 rings as was in this previous image. We want to visualize 1,000, tens of thousands rings. And ideally, the visualization tool should be interactive to help medicinal chemists really interactively navigate in this ring chemical space. So ideally, this would be a web-based solution. To start something like this, of course, we need to do the first step. And first step, we need to characterize our rings by some descriptors, by some numbers, because we need to, of course, process them in the computers. There are a large number of descriptors we can use. I suppose the fingerprints. This is a classical descriptor for cheminformatics, which is used for similarity searches and so on, would work very well. But I decided to use another descriptors called scaffold keys. I have very good experience. We developed them at Novartis a couple of years ago, and I have very good experience with these scaffold keys for characterizing rings and scaffolds for similarity searches, bioisosteric design. Because fingerprints have, particularly hashed fingerprints, have one big disadvantage. It is simply difficult to interpret the results. Even if the outcome or results based on fingerprints are very good, it is somehow not easy to understand why we are getting these results. And these scaffold keys, this is simply a set of 42 very simple topological descriptors characterizing the topological composition of our ring system, simply number of atoms and bonds of certain types, or number of atoms which are in rings, or exocyclic atoms or spiro atoms, properties of subrings, whether they are aliphatic, aromatic, size of the larger rings, type of fusion, and so on and so forth. I don't want to go too deep into the details. If you are interested, you can find full details in this article in this ChEMRX. This is open source article. Of course, one can calculate very large number of these topological descriptors. How I came to this 42? Basically, I selected this set of 42 parameters, which provided the most optimal recovery of bioisosteric scaffold that are described in medicinal chemistry literature. I told you that we developed these scaffold keys in Novartis. This was internal development. Also, the technology is fully described in this article. But I have very good news. This is a breaking news. This came just yesterday. Now there is an open source implementation of the scaffold keys available as KNIME node. It has been done by Steve Raffley from Vernalis. It is the part of this well-known Vernalis KNIME nodes. Steve, if you are online, thank you very much, because this is really excellent implementation of scaffold keys. It has also a graphical part, so you can see, really visualize on the molecules these different scaffold keys where they are located. You can, for example, on the link edit, yesterday link edit, you can find a link to this, this distribution. So once again, thank you, Steve. So I've calculated the 42 scaffold keys for my 40,000 rings. Here you can see example of performance of these scaffold keys for similarity searches. Simply these yellow scaffolds, these are the queries, and I simply calculated the similarity based on the scaffold keys from these 40,000 molecules. Here we can see the result, similar scaffolds. Those blue one are those that are reported in medicinal chemistry literature really as a bioisosteric. That means they're sharing the same type of biological activity. But of course, I'm not telling that these white are not bioisosteric. They have not been simply reported in medicinal chemistry literature with this type of activity. But I would say, you can see this by yourself, they are really very, very similar. So I expect that if they would be screened molecules with these rings, they would exhibit the same type of biological activity as these query rings. So now we have a big data matrix, 40,000 rings, characterized by 42 different descriptors, scaffold keys. And to visualize the data into 2 dimensions, we need somehow to flatten this data matrix into 2 dimensions. So something like this. This is the outcome of this exercise. There are, of course, many different methods we can use for the dimensionality reduction. Coherent network or self-organizing network, or this new modern method like Destiny or UMAP. We can use everything. But these, for example, this Destiny and UMAP, also coherent network, they have one common disadvantage. It is not possible to assign physical meaning to this axis, what is on the axis. So that was the reason why I used the old good classical principal component analysis. With principal component analysis, we can roughly interpret what is the physical meaning of these different axes. And I can tell you now, this x-axis, horizontal axis, is basically the size of the system. The y-axis, vertical axis, this is the something like feature richness or complexity. As I told you, this is, for these points represent 40,000 rings. Those that are bioactive, this means they are frequently used present in bioactive molecules. They are color coded. About 2,000 of these rings are bioactive. Again, color coding is based on these 9 target classes, which you can see this here, by the way. And another thing which maybe you notice, we can see these different colors are clustered into such a smaller cluster, like this green one, enzymes, or magenta one, GPCR ligands, blue one, kinases. This is on the other side understandable, because similar rings, one can expect that similar rings are clustered together, and one can also expect that these similar rings will have the similar type of target. And another thing we can see here, that this bioactivity is not distributed regularly in the ring chemical space. We can see several clusters, like the central cluster here, big, some smaller cluster here. It is another bioactivity area. On the other side, this border region, they do not contain many, these are more exotic systems, they do not contain too many bioactive molecules. And maybe you have noticed another feature of this chemical space, that this bioactivity is distributed a little bit diagonally along these diagonals. This has to do with this size and feature richness. So in this area, by the way, I hope you can see my mouse. Yeah. So in this area, these are right area. These are ring system with 4 simple rings. In the central area, ring system with 3 simple rings. Here we have system with 2 simple rings. And finally, on the left, these are very simple system containing just 1 simple ring. We can look at basically some small area. For example, we are interested in very small area, with large concentration of the bioactive rings, so we can focus on this area. Here we can see rings taken from 4 such small areas: magenta, rings active on GPCR ligands, blue kinases, red proteases, and green other type of enzymes. And we can see that really the scaffold keys cluster very, very similar rings together. Also, this color-coded, of course, they are known to be present in bioactive molecules. These non-color-coded are very similar, so one can expect that the activity of molecules having these particular rings will also be the same as of these rings with known bioactivity. So this is already a good tool for bioisosteric replacement. If we want to replace some rings with some not well-known ring and expect the same type of biological activity, we can use this tool for this. Another thing I tried, basically this was mostly for visualization of the global distribution of this activity in chemical space, whether I can identify or find some machine learning model that would classify these rings between active and inactive. I tried these 4 different machine learning models. I simply took the standard implementation from scikit-learn. Here you can see the result. I used 4 machine learning models: naive Bayes, nearest neighbor method, random forest, and neural networks. We can see that naive Bayes provide worst result, not very good. The best results are provided by standard neural network. And that already this comparison of the quality of the result can tell us something about the factors influencing the biological activity. If this activity or this distinction between active and inactive rings would be caused by just few simple independent parameters, the results of naive Bayes would be much better, because this is a typical case for naive Bayes when the results are caused by few independent parameters. On the other side, the best results have been provided by neural network. This means that actually these factors that are responsible for separation between active and inactive rings are not simple. It is really the quite complex combination of multiple keys, multiple parameters, probably non-linear combination. So the answer to my second question, which I asked myself at the beginning of the study, whether we can identify some simple parameters that are responsible for this classification between active and inactive rings, the answer to this question is no. There are no such simple parameters, some magic molecular descriptors. Really, this is a complex combination, non-linear combination of many parameters. And here are the results for this visualization of biological activity. I took the models calculated by neural network and color-coded this chemical space, which we have, chemical space of rings, which we have seen on previous image, based on the frequency of biological activity. And here we can see this, what I already told you before. There are several central clusters on the right, cluster with system with 4 simple rings, this biggest in the middle, the largest one. These are systems with 3 simple rings. Here, systems with 2 simple rings. And on the left, these are the most simple bioactive system with just 1 simple rings. These are just some examples. To give the chemist or everybody to chemist or cheminformatician, to everybody, a possibility to play with this data and to interactively navigate with this data, I develop a web tool. This web tool is available freely on the internet. Here you can see the address. And now I will try to show you briefly what one can do with this tool. Hopefully my video will work. This is always the risk of demonstration. So this is speed as it is really. So you can simply navigate through this chemical space, through this bioactive region, and go through these rings. This is really the biggest scaffold. If we are interested in some particular area when there is high density of bioactive rings, we can simply zoom to this area, as you can see this. So this system contains only, this space contains only 300 rings. Mostly we can see several blue points. That means these points are active as kinase inhibitors. So we can simply pick those kinase inhibitors. And the space in the middle, again, we can explore by moving the mouse. We can explore these rings. They have not known biological activity. It was not reported, but we can expect that since they are similar, they will be also active as kinase inhibitors. So we can, this is interesting spiro system, so we will pick it. Once we are satisfied, we can simply download these rings as a smiles. On the left, using this arrow, you will download smiles of this active system as well as this system which we picked. And this is another way how to visualize the data. These are the all 300 scaffold for this selected space. So this gives us some overview what is there. As I told you before, this web tools is available on my private website. You can see the address here. I have there currently 5 different web tools, and I hope some other will come. These web tools allows navigation in the chemical space of scaffolds, ring, and substituents. This allows to do interactive bioisosteric design, and one also can calculate different substituent properties, for example, Hammett sigma constants or Hunch P substituents parameters. Yeah, otherwise you need to look into the tables. I am not aware of any other tool when you can calculate interactively these Hammett sigma constants. As I told you before, these tools are free, available for everybody without any registration. So you may wish to try them. Well, I am not doing this for profit. I am doing this because it is fun. So that's the reason. So, and with this, I'm coming slowly to the end of my presentation. What I try to tell you, or what I have shown you, I did the chemolymphatic analysis of 40,000 ring system that have been extracted from 1 billion of bioactive and synthetically available molecules. We have seen on this graphical distribution that this bioactivity in the ring chemical space is not distributed regularly. We have several islands of bioactivity which are interesting. Unfortunately, I was not able to identify any really small, simple set of features that are responsible for the bioactivity of rings. Well, I suppose this could be expected. Otherwise, the chemistry and our chemolymphatic work would be too simple if this would be just set of simple parameters. We have seen that interactive web tools to navigate the ring universe is available. This can be used for bioisosteric design, hit finding, library design, whatever you think. All data I used in my analysis, this 40,000 ring system, with their target preferences, are available for download. And this is also another breaking news, which we learned yesterday from Markus in his excellent presentation. The magic rings went 3D because our friends from the Biosolve IT used this database of 40,000 smiles and used them as fragments in the CSAR system. They created 3D conformation, added the connection points, exit vectors. So these rings can be now used as fragments. Altogether, they created 15 million 3D structures, and they may be used simply as fragments in the design of 3D bioisosteric molecules. We can see we could see, if you remember, very nice example yesterday with one of these rings, which was part of GPCR active molecules. If I was not clear, or if you want to learn more about the system, you can find a publication. This has been published recently in this Journal of Chemical Information Modeling. This was this issue, which has been yesterday mentioned several times, this issue about large chemical space and navigation of chemical space. And of course, we have quite some time, I think, for questions. If you want to ask something, then I am here.